right, so now we're going to learn about a new reaction called the Wittig reaction. Wittig. It's spelled with a W, but I promise it should be said Wittig, like with a V, named after the German chemist who invented it. But essentially, it's a new way to make alkenes, and it selectively makes those alkenes. And it's kind of hard to see. There's glare off of one of the lights in my basement. But essentially, this is a CH3 right here. I see on the screen there's some glare. But that should be a CH2 of an alkene. So how does this reaction work? It uses something called an ylide, which is a type of Zwitter ion. So Zwitter ion is something that you guys have heard of before in the amino acid section. A Zwitter ion is something where there are two opposite charges on the same molecule. So amino acids are Zwitter ionic at a neutral pH. We have an amino acid, we'll just do glycine, is technically the carboxylate and the NH3 plus at pH 7. So this is Zwitter ionic. It has multiple opposite charges on the same molecule. So there's a negative charge there, a positive charge there. An ylide is a type of Zwitter ion. The negative and the positive are on adjacent atoms. So they're right next to each other, adjacent atoms. So this is the ylide right here. It doesn't look like we have any charges here, but we do have to remember that all molecules are not perfectly represented by a single structure. A really important resonance structure of what we have here is if we pull the electrons to that carbon. That gives an understanding of how this molecule might react. So that would mean we have CH2 with a lone pair and a negative charge bonded to pH3 plus. And sure, maybe you're like, why does phosphorus have a positive charge? That doesn't seem very stable. Well, it also has 3 different phenyl rings attached to it that could donate electron density to that phosphorus. And also, this is just one of 2 resonance structures, right? The carbon is also donating electron density to the phosphorus. So both of these structures are very valid, and this is the one that is useful in understanding the reactivity of this species. So this should be a time when you should be able to look at this and say, how is this going to react with a carbonyl? And you should be able to just predict it. How is that going to happen? So take a minute. Think about, how is this going to react with that? Because if you can reason it out yourself, it's going to be a lot easier to remember it in the long term. All right, you did that. You paused the video. You even drew a mechanistic arrow indicating how that's going to react, I hope. If you haven't yet, pause it and redo that. But essentially, we have negative charge on this carbon here. And how do carbonyls react with negative charges? Well, we have a partial positive on the carbonyl carbon, a partial negative on the carbonyl oxygen. So the negative flows to the positive, and that generates our intermediate structure. So that would have an O minus here. The carbon of the CH2 is now bonded there. And we have our pH3 here with a positive charge. So this would be our initial adduct. What should happen next mechanistically? What's our first rule of organic chemistry? Yeah, negatives flow to positives. Well, do we have any negatives and positives on this species? Yeah, the oxygen's negatively charged, the phosphorus is positively charged, so those electrons are just going to be added directly to that species to form a 4-membered ring. So there we go. We have our 4-membered ring. We have the products. So again, take a minute to pause the video. How can we move mechanistically from this intermediate up to that intermediate? If you draw it yourself without me telling you, you're going to remember it better. and you've paused and done that, and now you're back, and essentially we have to get a C double bond CH, so that can pull the electrons from there to do that, and then at the same time we have to get a PO double bond, and that can be pulled from this direction. So essentially that ring fragments. We have a four-membered ring. We know that four-membered rings have a lot of strain in them. To alleviate that strain, we're going to break that apart to form these products. Another important thing is I showed this as two distinct mechanistic steps, because I think that when you show it one and then the next step, the mechanism really makes sense. It really, negative flows to positive, then negative flows to positive again. That's really intuitive, and that's what I want you guys to concentrate on, is how intuitive those two steps are together. In reality, it's these two steps are actually concerted. They might be asynchronous, but they happen in a single transition state. So essentially, that negative charge adds to there, while this oxygen simultaneously adds to the triphenylphosphine to form this four-membered ring at the same time. It's not important that it happens. I mean, it's not like, the importance is for you guys to be able to push the arrows and understand why the product forms. And this is just a fact of the mechanism. It's been studied very well, and those two steps actually happen in a single step. So why is this favored? Why is the ball rolling downhill? Well, it turns out that we're essentially substituting out a weak phosphorus carbon double bond for a really strong phosphorus oxygen double bond. That double bond is extremely strong. So on your course packet, it says the reaction is favorable because of the strength of the blank double bond. It's that PO double bond that is really strong. So that is why the Wittig reaction is favored in the forward direction. So that's what happens to carbon. We make a ketone or aldehyde into an alkene. But we should also know how to synthesize this. Synthesizing an ylide is often necessary before you can perform a Wittig reaction. So that's where we are headed next. All right, so how do we form the ylide? The first step was we're going to form this phosphonium species where the phosphorus is positively charged. So what did we do? We took this triphenylphosphine, where the phosphorus has a lone pair of electrons. It's electron rich. It's a nucleophile. So this is our nucleophile here. And we're going to add some electrophile for it to react with. So this should be straightforward. What can we use to add 3 carbons? And this is going to be formed as a result, Cl-. Pause the video, write in what you think. It should be very straightforward based on everything that we've learned. All right, you've done that. Well, we need 3 carbons, and this is our nucleophile. It's negatively charged. We need a partial positive on a carbon, the carbon that forms the carbon-phosphorus bond. So we need an alkyl halide. So we would have the chloride generate that big partial positive, and the phosphorus is just essentially doing an SN2 reaction to provide our phosphonium product. So how do we form the ylide, though? This isn't the ylide yet. It's just got a positive charge, not a negative charge. More on that in a minute. All right, what did we do here? Well, this position right there is now negatively charged. How did we get that there? Well, it has 1 hydrogen here, and it had 2 hydrogens here. So we just did an acid-base reaction, essentially. Because the phosphorus is right next to that carbon, it significantly, probably 25 orders of magnitude, drops the pKa's of either of those hydrogens. So we don't need a super strong base. We probably could use a weaker base. But one of the standard bases that is just used a lot in industry and in labs in general to do this reaction is actually a really strong base. We call it N-butyl lithium. It's just the lithiate of butane. So essentially, I'll write N-butyl lithium. That's how people say it. But essentially, it's butane that has been lithiated. So it had a carbon-halogen bond. They added lithium to it, and that formed the lithiate. So this is what N-butyl lithium is. Again, we often draw it, I often draw it as the ion form because it has partial ionic, partial covalent bond character. But essentially, we talked a lot in chapter 20 about how this is a strong nucleophile. It's also an immensely strong base. So it is just going to do an acid-base reaction to form the ylide product. And the ylide can be drawn in the two-charge form, and we also have drawn it as the PH3 as the double bonded form. But these are just two different resonance structures. So that's how we synthesize the ylide. We do an SN2 reaction that we learned way back in chapter 7, and we do an acid-base chemistry reaction. That acid-base chemistry is technically chapter 2. So hopefully that makes a lot of sense. All right, now we're going to use Wittigs. So that's the next step.